everyone, and welcome to this presentation on reviewing very large protocols for TrustX Online 2024. Thank you, Rajiv, and the whole TrustX team to have us here. I'm very happy to present how we approach this important topic. But first, let me give you a quick intro about myself and Chain Security. So you can see me. I'm Matthias. I am the founding partner and CTO of Chain Security. I'm also someone who signs transactions. I'll go later into what this means in practice and why this reviewing very large projects doesn't end at a security review of the code, but processes further, because that's pretty important. But first, let me tell you quickly just a few words about Chain Security. So we've been in this space for, I think, 7 years, since 2017. And the team grew to around 25 people today. Most of us are based out of Zurich. We are kind of a double spin-off. We are a spin-off of the Technical University in Zurich, ETH Zurich, and we are also a spin-off of PwC Zurich or PwC Switzerland, which is one of the major audit companies. Now, we focus really on some of the most complex projects in the space, and our team, which is 90% technical, is really focused on uncovering new vulnerabilities and wrapping their heads around these very complex projects. We also really like to do more research. We like to contribute. We like to further the understanding of security in the space in general. And we are really also looking for new talent. Please apply at chainsecurity.com. And we'd love to find new riddle solvers of excellent skill to join our team. So let me continue. So what does it mean when I speak of large projects? I want to give a few examples. So we'll start with a very prominent one. The MakerDAO ecosystem, or as it's called now, Sky. You might have known they just rebranded, and let's look into it. So how large do you think the whole code base, if we just look at source codes of Maker, is? It is around 3,500 lines of source code. So this is based on the newest version. This is based on what was sent also for public code review in the latest code competition. Let's take another one, Euler. This one, also one of the projects we have reviewed, which then went through a code competition, has 4,500 source code lines, a little bit larger. Now, another famous one, Uniswap. Right, so also one which went through the crowd competition recently. Another one which has almost zero findings in a crowd competition. How large was this one? Uniswap V4, that is. It's around 7,500 source code lines. So this is really large, and those are examples of large projects. We reviewed a bunch of them. I can show you some. There are a lot more. Feel free to browse our website, obviously. We really like to write detailed reports about each project we review. And I'll want to focus on one specifically, the Enzyme project. We have been reviewing the Enzyme protocol since 2018 continuously, and this project has grown quite a lot. It is today one of the largest ones out there. We are looking at a total of almost 18,000 lines of source code, a lot more with comments. It's very well documented. It has 134 deployed logic contracts, 253 contracts overall. It uses basically everything which Solidity has to offer. So this is really, really one of these large projects out there. How do you review this, right? So it is a lot of thinking. How does this really look like? Let me show you. So I don't want to disturb. This is then what it really looks like. You just do a lot of pair coding, pair reviewing, and making sure you can cover as much as possible. So when this is done, of course, there comes time to write up the report. Actually, that's a continuous process during the whole review cycle. And I'll go over a quick part of the most important critical review activities done in such a large audit. So initially, you really need to divide the work. You need to come up with reasonable chunks. You will have a team, be it a team of 2 or a team of like 6. You have to divide the chunks, right? So this is usually the team sizes we work with. You have to continuously write down your assumptions, often implicit assumptions about the protocol. You have to check them. You have to review them with the partner, with the project itself. You build up that holistic system overview over time, and you fill in the holes and the understandings, and this is continuously growing, right? You have that challenged with your co-auditors and discuss it frequently. One of the most powerful things we do is this pair review, which you have seen in the video, where you actually sit next to each other, discuss the code together. And another part, which especially in these large code bases which interact with many different systems out there, you do get expert input. For us, of course, with a team size, we have a lot of that expert knowledge in-house, but also if you aren't in a large audit company, then you can often reach out to people in the industry to discuss these things, even on e-security, Telegram, and so on. People are usually very helpful to discuss these kind of matters with you. So do get this expert input. This is all critical in such large projects. And I want to stress the first point. Once again, you need to divide it into reasonable chunks. After all, you need to form an understanding of your code under review. And you can only do this if it fits in your head. And honestly, something like 8,000 lines of code, that is too large to fit into your head fully, at least in the time given for such a review. I'll now get into 2 critical parts which we use in audits before and after the core review phase. So we'll start with static analyzer. Static analyzer are systems which just take the code and spit out a bunch of warnings about it. So you can let them run initially. You don't need to have an understanding of the code yet. Then, of course, the core review phase is there, which takes up basically all of the time. But when you are done, it wraps up with deployment validation. Deployment validation being the topic, the project, or being the process which ensures that the code you have audited is correctly deployed on chain. Let's start with a static analyzer. So what is it doing? Like a static analyzer, I'll quickly run over this because you might be quite familiar with this by now, is a program which analyzes and inspects other programs using the code. It does not execute it. It can identify known bugs, security vulnerabilities. It can also help with standard violations. This is done fully automatically. And there are a bunch of approaches to this, which vary in their ability to give results of high confidence. So why is that different from other areas? Like if you do, for example, testing, you can validate that something is a bug, right? Because you wrote the unit test and it fails. And for a specific unit test, you can also prove that it's working, right? If there is no bug. There is symbolic analysis. This is a lot more powerful because it covers a range of inputs. Basically, you'd say like, hey, look, I read this unit test, but I don't define all variables. I'd basically say, hey, for this variable, it can be any value. And then always let me know if for any value there would be a problem. The static analysis, on the other hand, this doesn't take any inputs. So it just looks at the code, not at specific settings like specific variable initializations. For the kind of vulnerabilities which it knows about, it gives then a very high certainty to find them all. It has to over-approximate often, so this leads to a lot of false warnings. And obviously, it is not as powerful to detect all kinds of attacks because it can only reason about the code itself, not about the execution of the code. What is the problem in very large systems with this, right? So if you use a static analyzer, like I said, it can give out warnings which aren't accurate. And this is a run here of the Euler core. And this is after all the bugs have been fixed. This is the result of the code which has been sent to the crowd audit, the code which was fixed after the reviews from traditional audits. And what do you see here, right? You do see 75 medium plus vulnerabilities being reported by a static analyzer, right? And this is really a lot for a system which has 0 bugs, according to the best of our knowledge today. This is why today these static analyzers aren't that much relied on by teams because of this very high false positive rate, right? So we started out with this Securify in 2017. One of the first analyzers, static code analyzers out there, improved that with Securify 2. And since 2023, we are working on a static analyzer which really directly targets Solidity now, not the EVM implementation beneath. It's written in Rust, it's very fast, and it's very, very accurate. And this is crucial for these very large projects. And I'll go into some of its core features now. If, though, you want to have a really deep understanding of how the static analyzer we developed at Chain Security is working, I can really recommend this older recording from Anton given at DevConnect Istanbul in 2023. One of the features which this static analyzer is giving us is to reason about bundles. Bundles is what we call a system of smart contracts which interact with each other, where we know the code of all the parts which interact with each other. And they can call each other, they can call back, right? In general, these systems aren't perceived to be acting independently, and a lot of trust assumptions are made in these calls which call each other. And if you treat them as untrusted, the whole system would break. The benefits of such a bundle, just in short, are like reentrancy patterns become a lot more precise. In general, you'd have to say like any code to an external contract is untrusted. But if you understand what that external code can actually do because you include it in your bundle, you can reason about reentrancies and say like when they are actually become trusted. You can reason about read-only reentrancies, which naturally they have to call and be called back from other contracts. The external calls from one contract, they can be now annotated with what the other contract is doing to that return value. And this allows you to detect new kind of vulnerabilities where you'd know, oh, they've changed the setting. It's perhaps based on some thing like timestamps. And if we know that it has been based on timestamps, we need to warn depending on which kind of situation is happening. And overall, both by capturing these interactions and by being able to know all about the whole system, we can really holistically reason about it and find a lot of new things which were very hard to reason about before. I'll give you one example because it might seem a little bit abstract. A common source of vulnerabilities is incorrect handling of decimals. So you'd assume, for example, that a token has always 18 decimals, right? And this is mostly true, but sometimes not. And these sometimes are very famous cases, USDT perhaps being one of them. And in these cases, you really need to be careful. If you know that this contract is interacting with a contract which has balance, which has decimals which aren't 18, then you need to warn. But if you always only interact with tokens which have 18 decimals, you're fine. So in this example here, at the lower function, this balance, right? First off, it calls an internal function, balance of this. And there you can reason about, right? Because this is what you know in a static analyzer. But then you do an external call to the manager, and this also calls balance of. And now, is that something which has 18 decimals or not? Well, you don't know. But if you see it as a bundle, this is actually when you get to know that it does have 18 decimals or it does not, right? So you can really warn about this. Now, to be precise for static analyzers, it's really important to look into 4 different kinds of sensitivities. So the first one is a general one, flow sensitivity. Most static analyzers do this. This means you can reason about that something needs to happen before something else, right? So time matters. Don't give me errors if you see something and it's not a problem if it's being, for example, protected by a require statement before. Now, the 3 next ones are some things which are harder to encode and where, in general, false positives appear. So the field sensitivity means if you have an object, usually in Solidity, that be some struct, and you just interact with one of its fields, then you want to know that only interactions with that field are problematic, but not with other fields. Often instead, to make it simple, you have to taint the whole object and basically say, look, this struct touched some timestamps, and now any field looks like it's being touched by a timestamp, and we give out warnings. Object sensitivity is similar in the sense that here you'd have to report if you have 2 instances of a class of some contract or whatever, and you need to differentiate them. You need to track their process through the program. And the last part is like call context sensitivity. So here we want to make sure that only if a function was called, then we actually raise an alert, or we don't raise an alert, right? So and this is especially important if we know that inside some function we calling something is a problem, and inside some other function we call the same thing, it's not a problem, right? So you need to reason about the kind of the environment in which the call has been made. When you follow all of these requirements for precision, you do get a lot more accurate, right? And this is, in summary, what the static analyzer we use at Chain Security is doing for us to help us to get very accurate results we can rely on for very large projects, to find these bugs, these known kind of bugs. Now, we completed the manual review, we completed the automated review, the static analysis, we did the whole review. We think the code is secure, we passed over the report, it's deployment time. Now we need to make sure that this project is being installed correctly, if you want to think of it this way. And it needs to be connected correctly. All of these contracts, like in the example of Enzyme, we have like 100+ contracts, right? They interact with a lot more outside of Enzyme, obviously. They need to be wired up correctly, and any mistake here can be really critical. We need to validate that this really happened, and we need to be able to do it independently. And we want to enable this to be done against non-specialized nodes, right? That you don't need to run a special node which can do this, but that you can simply buy access to an archive node from a well-known provider and then run it against it, use your own archive node if you prefer that, but basically make it as trustless as possible. So this is our goal for deployment validation. A quick overview of all what we have seen, what happens if deployments go wrong, right? So there was, for example, once a Tornado Cache governance proposal where it wasn't clear that this was a malicious proposal, right? So they took over basically governance and got away with 2 million. There has been a broken USDT token set up for the precursor of what is Yearn today, iEarn, and this has been broken since deploy. This was really a long time ago. This cost the project 11 million. A more recent hack of a malicious deployment by the developer itself was on a project called Munchables. They had to even hold the chain to prevent bad actions happening here. And this was an upgradable proxy, and I'll go into this itself, what happened here in a few slides. 60 million was lost here. And an older hack, but given its size and its complexity, an important case where you'd have an upgrade, and the upgrade would actually introduce a bug because of the previous version having initialized a storage slot. So this led to 190 million being lost. And just a very recent case, a hack happened where approximately 1.7 million were lost. This was after an audited code was then upgraded, which wasn't audited, and then deployed. As I said initially, I'm also one of those who have to sign transactions to make sure a project stays secure, right? And this can be really hard, right? What do you do, right? Do you trust someone else has signed this off correctly? Or do you take the time to validate yourself? And if you validate yourself, what do you actually do, right? So we saw that this is not scalable in practice. And this is why we came up with deployment validation to help us. A quick overview of all the things you have to think about when you want to manually validate that deployment is correct, right? Has it been incorrectly configured? Has the wrong code been deployed? Has it perhaps even been a malicious deployer, someone who's tried to sneak something in? Is because of some script error, the deployment incorrect because it's incomplete? This might happen easily if some system hasn't been initialized, but it has been deployed, right? Now, accidentally or on purpose, has unaudited code been deployed? Or has it been state previously in an upgrade and now the new state breaks, the new functionality breaks because of the historic state? All of this can and has happened before. This case about the malicious deployer, the Munchable exploit, what happened here was you'd initialize a proxy, but you pointed to an unverified implementation. This then executed some things, and in this case, it gave the attacker a large balance of the token without emitting any event. Then you upgrade to the benign implementation, you hand over the admin access, you give it to the project, and on a Block Explorer, everything will look fine, right? The code has been deployed, validated, it's pointing to the right thing. There are no malicious events being logged of something being deployed before. There is just that one thing, which is this implementation, which has changed. Now, obviously, the malicious deployer waited until funds have been committed and then withdrew them with their large, hidden balance. So what could you learn from that, right? You could say oh, look, we have to look if proxy implementations have changed, and if those are unverified, then we need to be very cautious. Yeah, you could say that, right? But there are even more sinister approaches to sneaking in something in a deployment transaction itself. Just a quick rundown here. If you deploy, then what happens is that the output of this initial call is saved as the bytecode. This is how create and create2 work. The constructor, which as its main goal has this task to output the bytecode which needs to be deployed, has at this time full access to the state of the smart contracts which are to be deployed. And the constructor is not part of the deployed bytecode itself, so you can afterwards validate the code while it does not validate the constructor. So all of this means a malicious deployer can sneak in during deployment basically any state change into the system, and this is simply how it has been designed. So to be able to validate deployments, you need a lot of things. You need to validate, of course, that the correct bytecode is there, the code you have audited, right? This usually should refer to a Git commit. You need to validate the trust model. You need to make sure that you didn't configure it wrongly, that you had the same assumptions during audit than what happened during deployment, right? I mean, a trivial case, you might have thought they'd point this to some multisig to now allow for secure admin access, but they pointed it to some EOA where it's not as clear what that EOA is actually doing. You want to detect, of course, suspicious admin activity, like I said before. Some time ago, you'd have to warn if self-destruct in create2 is possible, but this is gone now. You need to make sure that upgrades are trusted, and you need to make sure that any third-party smart contracts which this system is interacting with are set to the correct ones. It's just a list of things you have to do. And to make that like as easy, as painless as possible, we introduced deployment validation files. This is just a simple file describing the state of a smart contract. It can be validated, it can be generated, it can be validated trustlessly by anyone. This is really important from the project perspective because they want to know they deployed everything correctly, right? They don't want to make mistakes. They send off their transactions to set up the system, but we know that like in this distributed systems, you can never really rely on that it was all done correctly and safely, right? And once you have deployed it, you want to have that final check to know, oh, it does look good. From an auditor, you want to know that what you have audited has been deployed as you expected it, right? This is both referring to the code you have audited, but also to the settings. At this point comes the truth, I'd say. You do validate that what you thought the project is doing is actually doing, and you might catch some misunderstandings which slipped by. Keep in mind that usually deployment scripts are not audited. Usually only the Solidity code is audited. So this allows, while not auditing deployment scripts, it allows to audit what has actually been deployed in the end. Now, there are some other perspectives. Users, they want to know what this contract is actually doing. DAO voters, they want to know if they can upgrade to that new contract, and they want to also know what is it doing. And integrators, they want to know what is a safe setting, which parameters do they rely on to use that smart contract correctly. They, of course, also want to know that they don't accidentally use an older version or a version on a different chain or basically anything which makes it so hard to point to the right addresses. Our solution to this is a deployment validation file. These files, they describe the expected on-chain state. They ensure that the code in a Git repo is the one which was deployed. They also validate critical contract state. So this often refers to implementation of proxies, but it's basically a lot of things which have been set during deployment time. And afterwards, they document critical contract history, like which addresses have been minters, for example. And this way, you can detect if something changes. And they also document the dependency to other contracts. And this dependency to other contracts is actually something which can over time change, meaning if a contract you depend on, like USDC, is being upgraded, you might not believe your deployment to be safe anymore, and your system might even break depending on the changes which have been done by those contracts, right? So you can, in effect, say that your deployment is safe only with a certain set of contracts on the other side. Let me show you how this is done. So you run the tool, and it fetches the storage snapshot from the archive node. By the way, the archive node in this case, it's simply a small NIC which runs. It's one of the nice hardware provided by Deb nodes, right? So we get all of that and we decode those events. You, of course, first check, is the bytecode correct? Yes, looks good. Is everything we configured as immutables correct? Right, you might have here some specific settings, especially the decimals, as mentioned, are important. We decode those into meaningful values, which are much easier to read than the hex values, of course. So overall, you can validate all of these critical contract state. You can validate the events, and you can check, was this done at the correct block height? Yeah. Overall, all of this allows you to get an idea of, is that contract secure, right? At the very end, you might even say, like, this is an insecure contract. We know it's insecure, right? So all of this is possible. I'll quickly show you one example how this really looks like. So you can go to Chain Security's GitHub, go to the DB files where we have uploaded a few. Let's look into Enzyme's Arbitrum deployment. And perhaps in case a lot of people are familiar with, let's say the Uniswap adapter, right? Uniswap v3 adapter. So here, this has been deployed, validated it, right? It's the correct code, but also, for example, did this point to the right router, right? So, for example, we can validate that this setting is the one which Uniswap says is the correct one. Yeah, so this is the swap router, which we can validate on their homepage. So we also give these names so that you don't actually have to look it up. These are local names, right? You'd have your own idea about what they are. And finally, you can add additional data. Here we sign also that we did audit this. You get a security contact, so if there's something wrong, you can reach out to us or Enzyme, of course, and you get a link to the audit report. A high-level overview of this is the DBF. It gets created after deployment, right? So you deploy your contracts on chain, you configure them, which can happen in multiple further transactions, and then you create a snapshot of the state, and this creates your deployment validation file. And at this point, you'd also sign it, right? And you'd have now this validated signed deployment validation file, which users can validate at any further point in time. In summary, for deployment validation, what you need to remember is that projects, they can validate that their state has been deployed correctly. Auditors can easily see what's going on with the deployment and can validate it without needing to review custom deployment scripts. Users can quickly check if the deployment which an auditor or the project itself has signed is still the actual one. And for example, DAO voters, they have an easier time to make informed decisions. Integrators have an easier time to link to the correct code. And all of that is targeting that projects, be it small or large, but especially for a large one, where these interdependencies are so uniform and so complex, that we can really ensure that everything has been deployed correctly end to end. So those two systems, the static analyzer and the deployment validation, those are what we use together with a lot of manual review. Thank you very much for listening to this. Feel free to reach out at any point in time. We are available, Twitter, Telegram, the usual channels, and especially if you're interested in deployment validation, you can give it a try yourself. This is open source code at Chain Security/deployment validation, and we are happy for any feedback to improve the project. Thanks a lot.